Consider the electric field coming from a long, thin, uniformly charged wire. This was solved using integration with Coulomb's law, but with Gauss's law it is possible to find the field by an almost trivial calculation. If the wire is very long and we are not too near either end, then by symmetry the field lines outside the wire are radial and lie in planes perpendicular to the wire. Also, the field has the same magnitude at all points at the same radial distance from the wire. This suggests we use as a Gaussian surface a cylinder of arbitrary radius r and arbitrary length l, with its ends perpendicular to r as in this diagram. So we have a Gaussian cylinder here. We're going to use an imaginary cylinder, Gaussian cylinder, and with a radius of r and a total length of l. Now if we say that lambda is the charge per unit length of the wire, so we're going to say that's the charge per unit length, the charge within the Gaussian surface is simply lambda times L. So that's charge per unit length times the length, which obviously gives you the charge, the total charge along this wire. Since the electric field E is at right angles to the wire, so the electric field is moving at right angles, sort of like this to the wire, the component of E normal to the end faces is 0. Since the electric field's going like this, if you like, then there's no component of E coming in this direction and there's no component of E going in that direction. So the normal components to the ends are 0. Thus the end faces make no contribution to the integral in Gauss's law. And at all points on the curved surface, E perpendicular equals E, and it's a constant value. In other words, the electric field perpendicular is actually E, and it's the same value at every point around the surface of radius r. And since the area of this surface, so if we look at this, we know that through ordinary geometry that the area of a cylinder is 2 pi r, in other words the circumference of a circle multiplied by the length. So we have the surface area of the cylinder, we have the electric field here, E, so we know that the flux equals the electric field times the area, so that we can write this here: the electric flux equals the electric field times the area, and we know that the total charge, using Gauss's law now, we know that the electric field times the area equals the total charge enclosed by this divided by epsilon naught. Well, we know what the total charge, it's lambda times L, so then we can immediately plug these values in and rearrange to find E, and it turns out the electric field E is 1 over 2 pi epsilon naught times lambda over r. If we note here, this is exactly the same as we did before with the very complex integration we had to do using Coulomb's law. So this is a much easier and faster way of calculating the electric field from a infinitely long wire.